Okay, welcome my dear students. New class. In the last class, we discussed about the some examples of the matrix representation of a linear transformation. In this class, we discuss some properties of a matrix representation of a linear transformation. First, we just check whatever this we have this prove this theorem. Firstly, let V and W be two finite dimensional vector spaces, ordered basis B and C respectively, and S and T are the two linear transformation. Then S plus T matrix representation of a S plus T corresponding the basis B and C is the same as a S corresponding to the basis B and C, and plus T corresponding the basis B and C. And also if we take a scale, because we know that the sum of a two, if we have S and T are a two linear transformation, then S plus T is also is a linear. And similarly, if lambda is any scalar, and then we can say the lambda T is again is a linear transformation. So here is also we have take a lambda. So this is I think so this is not alpha, this is lambda. So this means lambda T B to C is the same as the lambda times of a T of B to C, where lambda is any scalar. So this is a mistake here. This is nothing but this is a lambda. Okay, we tried to prove this because we start from take a S and T be a two linear transformation, and if S and T be is a, this idea is a proof is very simple. We have a S from V to W is we have a linear transformation. Then you know that the S of this is B of C is nothing but is equal to, you can just write as a some alpha I j times matrix representation of this accordingly to the order of the this dimension of this basis. Similarly, we have to take a T, and then we have to S and T, S plus T, and then S plus T is again V to W. Then we define how to S plus T we have to define. So S plus T is nothing but is equal to, we define S plus T V is according to our definition. If S is a linear transformation, T is a linear transformation, then S plus T can be defined in the form of a S of V plus T of V, and then similar fashion we can use this techniques to prove this. Okay, let's prove that. Let B is equal to V1, V2, Vn be basis, and C is equal to W1, W2, Wn be the basis of a W. And now I take a T of Vi can be written in this form. How this is written in the form? Because we take some Vj, V is the element of a, we have a this vector space V. Then this V can be written as a finite linear combination of the elements of this alpha 1, V1, and so on, alpha n and Vn. And then we can say that this is a coordinate vector of this nothing but is equal to, you have a alpha 1 up to alpha n. Similarly, we can say that if we have to operating the T here, so we have a T of V is equal to, you have a alpha 1 1 T of 1 1, and similar this is suppose we have to take a corresponding to W1, we have a this one of the vector can be written as all the linear combination of a W also. So that means we can say that also you also know that T of U is T of V is equal to is equal to T of Vi is equal to, you have a Wi, and then we have a linear combination of this form. So this means this, if you remember, I just show that where matrix representation in the form I just take this is T of V1 and T of V2. So T of we have a V1 can be written as a this is the T of V1. Okay, this idea is simply is this form. You know that T of V1 is the element of a W. Then T of V1 can be written as a linear combination of the elements of this. So alpha of alpha 1 1 W1, alpha we have a 1 2 we have a alpha 1 W2, and then so on we have a alpha up to the m. So I is equal to 1, so m, so you have a m, we have a m okay 1 1, so 1 2, and then you have a, we have to just say that 1 into m and Wm. Similarly, we write it V2, and then take of all the sum is there, then we can just take a matrix into this form. So T of Vj, jth entry of this is the form of a this form. So this is T of Vj is equal to the similar fashion we can define, because S is also you have a V2 W is a map. So this means this corresponding to the basis is equal to this, because we know that we can write the column vectors. So T implies that T is the form of alpha ij. J can be written in the form of 1 to n. In the similar fashion, we calculate the S of Vj. S of Vj can be written as some another scalar beta I beta j. So this means we can say that similar fashion, S of V have to B and C is nothing but is equal to, you have a beta times of a I and j. So this means this written in the form, I just say that this is S written in the form of the alpha ij and beta ij are the unique scalar, because this representation is a unique according to this order of the basis. We take a order of the basis in according to the order of basis. This representation is a unique. Now we try. We already know that this. Now take a sum of these two. So now we define S plus T. Now S plus T defined into this form, and now you that's the S of Vj you can write is the sum of, you have a right here here sum of I running 1 to m beta ij wij. So this means we can say that beta ij wi wi, then you have a wi plus you have a sum of alpha ij, you have a wi. This means you can say the sum of, because some are running the same value, so beta ij plus alpha ij and wi, and that means we can say that S plus T corresponding to the basis B and C is nothing but is equal to, you have a beta ij plus alpha ij. So this means clearly we show that this means sum of these two is nothing but is equal to beta ij plus alpha ij. So this means we can just say that in the form of this. So S plus T is nothing but is equal to this, and now this is nothing but is equal to S, and this is nothing but is equal to, we have to prove that this. So that means we can say that S plus T matrix representation of a sum of a two linear transformation basis corresponding to the basis B and C is the same as a corresponding matrix of the corresponding to the S plus the corresponding to the matrix corresponding to the linear transformation T. So this we have to getting the proof of this theorem is we have a complete. Okay, so now another part of the proof is also similar fashion. We can just try for a lambda is be a lambda v. Then we have a clearly alpha of lambda v is defined into the this form. So we have to take a here. This is a lambda. Sorry, this is lambda. This is also lambda, because we have to choosing the lambda. This is, I'm sorry, this is lambda everywhere. This is lambda, and then okay, this is finally I just say that this is lambda, this is lambda, this is lambda. Okay, now I just take, if this is written in the form of this, so the lambda of t corresponding to t is equal to, you have a lambda times of this, and then this is nothing but is equal to, this is what, this is nothing but is equal to, this is corresponding to the basis of a t. If we have a t from v to w, then clearly t can be written in the form of a sum of t of Vj, T of Vj can be written as the sum of I running 1 to m, and then you have a alpha ij and w I. Then we can say that T of V, T of B and C is can be written as alpha ij. So substitute the value for alpha ij is equal to T. So finally we getting this. If we have a like this form, we can say that clearly this transformation into this form. Okay, so now this completes the proof of these two properties. So that means we can say that if we have a S and T are a two linear transformation, so we can also find the matrix representation of this sum of a two linear transformation and scalar multiplication of a linear transformation. Okay, now we discuss this how to by the example. We have to verify this theorem by example. Also, we take a two linear transformation. I take a v1 v2, this t of v is equal to this form r2 to r3. Then we have to just you have a r2 to r3, and then we have a this is both the transformation is r2 to r3. So this means the basis of a b and c. So we have a b is the basis is equal to standard basis we take in the form of e1 and e2, and C we take in the form of a E1, or we take some F1, F2, F3 form. So we have a F1, F2 and F3. These are the identity matrices. So identity, this is standard basis for this. So we just try to find the first, we find the what is our S plus T. S plus T of, you have a V1 plus V1 comma V2 is the form of this, is the form of S of V1 V2 plus T of V1 V2, and now S of V1 V2 is equal to twice V1 plus 4 of V2 comma 0 comma 3 1 minus 5 V2, and then we have a plus is equal to V1 minus twice V2, and we have a 3 V1, now 4 V1 plus 3 V2, and this is nothing but is equal to 2 V1 plus V1 is equal to, you have a 3 V1, now plus 4 V2 minus 2 V2, you have a plus cut twice V2, and 0 plus 3 V1 is equal to, you have a 3 V1, and 3 V1 plus 4 is a 7 V1, and then minus 5 and plus 3 is equal to minus cut twice V2. So this is S plus T. Now we calculate the S plus T over the E1. So just take a, I take a, okay, just the next slide. So S plus T is this form. So now we have a, this is the form of a, this 3V1 plus 3V, I think this is 3 plus S is equal to this. So V1 plus 3 and minus ka plus ka 2 plus ka 3 4 3 7. This should be this is wrong. This is I think this should be is equal to, you have a minus ka 2 times of a V2. So this means we have to take a, this is minus ka 2 times of a V2 in this form. So clearly this is by mistake, because we have to adding these two. So this should be minus ka 2 times of a V2. So if we just take a S plus T, so we take a S plus T over E1 is the form of a, this is equal to, corresponding to E1 is equal to, you have a 3 3, you have a 7, and this can be written the, this is the written in the form of a 3 3 7. Okay, so this can be written as a 3 times of a F1 plus 3 times of a F2 plus 3 times of a F3, and this is nothing but is equal to 3 times 1 0 0, 3 times of a 0 1 0 plus 3 times of a 0 0 1, and then we have to just say that ST plus T corresponding to E1 is corresponding, the C is a column vector, you have a 3 3 and 3 sorry 3 3 7, you have a 7, so you have a 7, and a similar fashion we calculate S plus T over E2. E2 is the form of a, like this, you have a 2 and 0, you have a this is first one is equal to 2 0 minus 2, and this can be written again is equal to 2 times of F1 plus 0 times of F2 minus 2 times of F3. Then we can say that this is corresponding to the 2 0 minus 2. So this is, we can say that 2 0 minus 2. So this is the sum of this form. Now separately we calculate the S of this. We have to S corresponding to the S, we have a this. So S corresponding to this, we have a this clearly, if we take a S corresponding to the B and C is equal to, you have a column is equal to 1 3 4, and then you have a minus 2 0 and 3. So this means we just said that this minus 2 comma 0 and 3, and similarly we calculate the T. T of, we have a B or C is the form of a this is nothing but is equal to corresponding to the column is equal to, you have a twice 0 3, and then you have a 4, because in the standard basis 0 and minus 5. So 2 0 3, and then we have a 2 0 3 4 0 minus 5. And now if you have to adding these two, then you can just say that we have to take a S of B and C plus we have a T of B and C is nothing but is equal to matrix this plus this is equal to 3, minus 2 plus 4 is equal to you have a 2, 3 plus 0 is equal to 3, 0 plus 0 is equal to 0, 4 plus 3 is equal to 7, 3 plus minus 2 is equal to minus 2, and this is nothing but is equal to same as a S plus T corresponding to the B. So that's why we have to verify that the result is true in this case also. Okay, I will try to one more example. Okay, just we have to just take it the polynomials case, very simple class. I just take it. I take S of A plus Bx and T of A plus Bx is defined in the form of a like this. I just simplify also A plus Ax Bx square B plus B plus Ax B. This is again you have a sorry this is nothing is a B. This is sorry this is clearly correct. I take a B plus Ax plus x square and this is defined this form. So first we calculate corresponding to the basis. So we have to calculate T of 1. T of 1 is only the constant term are there. So this is constant term are there means we have a this is can be written as a this is T can be written as a 1 plus 0 into x, and this can be written in the 1 plus 0 into x can be written as a 0 plus 1 into x plus 0 into x square. So this is 1 T of 1 is equal to you have x. If T is 1 it can be written as 0 into 1 plus 1 into x plus 0 into x square. So this means we can say that T of 1 can be written as 0 1 0. Similar fashion we calculate T of x. T of x can be written as a T of x can be written as a 0 plus x, and this is nothing but is equal to 0 plus x means 0 plus 0 into x plus we have a 1 into x square. So this is nothing but is equal to x square. Then we have to test T of x corresponding to the C is we have a column vector is 0 0 1. So this means we can say that T with B and C is equal to we have a 0 1 0 0 0 1. This is for T. Now similar fashion we calculate the S. So we just take a similar fashion we calculate the S. S is equal to we have to in this form. So this means we have to calculate S 1 plus x and x square. So 1 plus x means we have a 1 1 0 and x square means we have a 0 0 1. So this means ST is equal to 1 1 0 0 0 1 form, and T I already explained you how to calculate the T. So T is in the form of this is equal to sign. This is equal to this form. So Tx is equal to you have a this is 0 1 0 1 1 0 1, and then we can say that T of BC is equal to 0 1 0 and this, and now if we adding these two then calculate the S plus T. So S T S1 S2 S1 is equal to this plus is equal to, and then S plus T is equal to 1 plus x square, and then we can say that B is equal to 1 2 0 1 0 2, and then we have to S plus T is equal to this. Now clearly this if we take a is equal to this plus this is equal to the same matrix. So this is satisfy this condition. So this means we can satisfy this. It means this is theorem verified by these two examples. Now I just try to one more result when we have a in place of a addition of a composition map we have a composition of a linear. So we have a T from U to V and S from V to W be a linear transformation. So you have a U to V and we have a V to W is S. So this is T. Then we have a ST is a map from. So you have a clearly ST is a map from U to W. What we do this if we can say that these two are the linear transformations of vector of dimension m, n and p. So the U is a dimension m, V is a n, and W is a dimension for p respectively. And the ordered basis we have a B, C and B double prime. So then we can say that this is ST is a B double prime is the same as a S of C of B double prime and T of B into C. So this means we can say the composition of a linear transformation can be written into this form. Okay, so we try to prove this result again using the same technique. We have to already to S and T are a two linear transformation. So this is already we have to calculate these two matrix representation, and then we have to calculate what is our composition is defined, and then in this form. Okay, so they take we have a, because U is a dimension of a M, V is a dimension of a N, and W is a dimension of a P. So we take a B is equal to U1, U2, UM be a basis, C is equal to V1, V2, Vn is a basis, and B double prime is equal to W1, W2 and W2 be the ordered basis. Let T of some UK is equal to, we have defined in the form of the previously just as it is T of U1 can be written as a, because T from U to V is written as a some scalars into this linear combination of these vectors v1, v2, vn. So this can be written in the form of a j running 1 to n. So we have to just say that if k is equal to 1, so we have to say the u1 can be written in the form of a alpha. We have a k is equal to 1, so this is the written in the form of a sum of j running 1 to n alpha j is equal to 1 1 k, sorry, k is equal to 1. So this is can be written in the form of a, sorry, this is written in the form of a sum of j running 1 to n. We have to take k is equal to 1, so alpha j 1 and vj, and this is if we have to j is equal to 1, so alpha 1 1, and then you have a v1 plus j is equal to 2 alpha, you have a 2 alpha j is equal to 2, so you have a 2 1, we have a v2, and then you have a so on, alpha is equal to n, so alpha is equal to n1, and we have a v of n. And so this means we have to similar fashion we calculate the next is a u2, and so on. The kth term in this can be written in the form of this. Similarly, we can write s also, because s is a map from v to w. So this basis can be written that this sub beta j into wj. So this is simply is equal to this form. Now from this we can say that t of this b and c is nothing but is equal to, you have a light is a alpha of jk, and then you have a s is equal to, you have a b and you have a basis accordingly, you have a basis c2, you have a b double prime is equal to in the form of you have a beta of ij. This form we can write, and then we have to just write into this form. Okay, so this clearly is here. So t of b of c is equal to, you have a j and k, t of s of c into b double prime is equal to alpha of ij. And now we calculate the composition of two maps. You note that how to calculate the composition of this s of t of a uk, and then t of uk is equal to, you have a sum of this jk vj, and now apply this is a beta this is we have a again apply the alpha. So this is alpha j is a constant, it's come, and then we have a s of vj and apply the condition for, you have a vj. So vj can be written in the form of a this is sorry, alpha ij is missing here, this is alpha jk, so alpha times jk, and this is equal to this thing. So now we have to write this alpha jk I take inside, and then w is I equal, this is also, you have alpha of jk here missing here. Okay, this is here. Okay, so this means we can write into a this form. Now because of this sum, we have to just state that gamma ik, where gamma ik is nothing but is equal to, we can say that the sum of this thing. The sum of j running 1 to n beta ij alpha jk is, we have to say that is a gamma of j. Now we have to just take composition is from u to k uk. So we have to uk means we have a b, and then composition of corresponding to the basis of a b double prime. So that means we can say that this is b double prime. So this means this is gamma gamma of this ik, and gamma ik is nothing but is equal to, you have a alpha ij beta ij. Now you just see that beta ij is nothing but is equal to, we have to calculating here sorry here beta this is equal to beta ij is nothing but s of this, and then we have a this thing, and then t is equal to this form. So we substitute the value for these two, and then we can quickly getting into a this form. So this means this we can say that this is complete the proof of this, where we can say that this composition of this. Now you see clearly this is the because of this composition map we have a from u to w. So this is the basis for a u, and this is the basis for a w, and as is a you have a from the basis from v to w. So this is the basis for v, this is the basis for w, and t is the mapping from u to v. So this is the basis for u, and this is the basis for v there. So this way we can say that this means composition of a two linear transformation can also be represented in the form of this s times into t times of this thing. Okay, so try one more example by this thing. So we take a P2 to P3 is a T, and S is a P3 to. So this means clearly you have a this is P2 to you have a P3, and P3 to you have a P2. This is T, you have a S. It means ST is a clearly is a map. So ST is a map from P2 to P2. Okay, so basis standard basis we have to calculating. So we have to just say that T of Px is nothing but is equal to integration of this. S of Px is equal to you have a derivative of a Px there. Okay, so we just first try from T of 1. So we have a T of we have to calculating the basis of a B because of a P2 is this is the basis for P2, and this is the basis for P3. So this means in this case you have a B and you have a B double prime are the same, and this is here you have a C is there. This means we can say that this C as it is, and B is the same as a B double prime because we have a mapping from V2 to V2. Then we have a basis are the same. Okay, so we calculate first is a T of 1. So T of 1 means 1 into dt is equal to T, and then we have to take a 0 to 1. So we get T of 1 is equal to you have a clearly is equal to x. So T of Px we have to define integration of 0 to x. We have a f pt, and we have a dt. So now we have a next is we take a T of x. T of x is equal to 1 by 2 x square, and now we have a T of x square is equal to 1 by 3x cube. Okay, this is square, and then we have all these things equal to this. So this can be written in the form of a x square. So this can be written as a 0 into 1 plus 0 into x plus 1 by 2 into x square plus 0 into x cube, and this can be written in the form of a 0 into 1, 0 into x, 0 into x square, and 1 by 3 into x cube. So that means we can say that the matrix of this and this matrix T of this corresponding to the basis we have a B to C is equal to we have a clearly is equal to we have a 0 0 and 0 0 sorry 0 1 0 0. Now we have a 0 0 half and 0 0 0 0 1 by 3. Okay, so this means we can just say that into this form. So this means we have a just calculating this matrix into a this form. Now similar fashion we calculate the s is nothing but the derivative. So we have a derivative of 1 is equal to 0. It's written in the form of this. Derivative of x is equal to 1 is written in this form, and derivative of x square is equal to 2x is written in this form. So we can say that this s is nothing but is equal to is s is c to b. This can be written in the form of a matrix is equal to 0 and 0 and 0. Then you have a 1 0 0. Then you have a 0 2 and 0. This is matrix. Okay, this is the matrix of a C2 B we have to calculate it. Now we just check whatever about our composition map. Composition map, you know that composition map is defined from P2 to P2. So we have a composition of a map. First we define the what is our composition of a map. If we take a product of these two, then product of these two is simply is equal to an identity matrix. Okay, so now as composition T1, so as time T of 1, and T of 1 is equal to, you know that is a T is a integration of a 1 is equal to x. So this means t of s of x written in the form of a derivative of x is equal to 1. So this is into this form. Similar fashion, we can calculate st x as t of x as of as x the integration of this is 1 by 2 x square, and then if we take a derivative of this, again you have a x. So we have a 1 by 2 into we have a 2x, this is equal to x. So this means written in the form of this. Similarly, we have to take is a x square, then we have to integration of the 1 by 3 x square, then we have a derivative of the 3x square 3x square, and then we have a 3 is cancel out into this form. So this means we can say that st we have a b2 b is equal to we have a matrix is equal to you have a 1 0 0. Now we have a matrix is equal to 0 1 0, then we have a matrix is equal to 0 0 1, and this is the same as a matrix of a S C to B. So this means ST is identity matrix, so we can write S is C to B, and then we can say that T of you have a B to C. So this verify this the theorem. We have to prove this. I did try to this thing is equal to clearly this is a STB to B. So we just say that this is clearly we complete the solution of this problem, and then after this this means we have to now I have to stop today's class here, and in the next class we have to discuss the how if we have a matrix representation is given, how to matrix representation can be if a matrix representation is given, how can write as a linear transformation of such a matrix. If we have a matrix is given, then we have to write as a general linear transformation, means is the matrix associated with the linear transformation. Here the linear transformation associated with the matrix. So we have a now we have a linear transformation is given, then we have to find the matrix a matrix transformation. We have a matrix is given, then how to write is a linear transformation of this corresponding to this vector species there. So we discuss this thing into a next class, and also try to prove one more result related to this. So now I have to stop today's class here. So thank you very much.